Okay, I think we can start. Welcome everyone to MLFL. For today, it's my pleasure to introduce our speaker, Xiaolong Wang. So Xiaolong Wang is an assistant professor in the ECE department at the University of California, San Diego, and a visiting professor at NVIDIA Research. He received his PhD in robotics at Carnegie Mellon University. His postdoctoral training was at the University of California, Berkeley. His research focuses on the intersection between computer vision and robotics. His specific interest lies in learning visual representations from videos and physical robotic interaction data. These comprehensive representations are utilized to facilitate the learning of human-like robot skills with the goal of generalizing the robot to interact effectively with a wide range of objects and environments in the real physical world. He is the recipient of the J.K. Agrawal Prize, NSF Career Award, Intel Rising Star Faculty Award, and research awards from Sony, Amazon, Adobe, and Cisco. So without further ado, let's welcome our speaker.
Thank you. Thank you for the introduction. Thank you for having me here. I would very much like to do it in person, but it's just there's only two of us to take care of my daughter at home, so I cannot really travel right now. All right, so I'm going to talk a little bit about our work focusing in humanoids in UCSD, and let me actually start the timing. I'm Xiaolong, and this is my actually previous house. So it basically has become a long, at least maybe now it's better, maybe 1 year ago, this is the long that basically every weekend we will need to clean up this mess. So a lot of my research basically motivated from life I'm experiencing, and given these scenarios, it just come to me that we can basically do a demonstrations with the robots we have. So this is a demonstrations we did a while ago. So this is, I would call this is a toy example in the sense that it is picking up toys, and also the environment is not as messy as it was in the previous picture. So it's like a little bit staged, kind of simple environment. And here is my daughter watching Peppa Pig. But if you look closely into this like robot, you actually kind of realize that this robot is actually a little bit large. And particularly if you walk the robot in the hallway, it's almost taking the whole hallway. It's very hard to actually make it fix in a regular house. So one thing we can do is to buy a bigger house. So that's probably not very scalable. That's doable, but not very scalable. And then the other way we can do is basically try to squeeze your robot a little bit. So that's essentially why we think all these humanoid robots, the big argument of why humanoid robot is useful is it's actually very slim, and then you can work in very narrow environments and then do things that humans do. So wherever there's a humanoid robot there, and then there will be always discussions. Oh, why do we do legs? Why don't we do wheels? So there are certainly scenarios that legs are going to be more robust. Like a lot use case people use is walking upstairs or step over some barriers, like different toys in the home, which might be sometimes stuck in the wheels. But fundamentally, the way I see is actually so because the bipedal robots still does not work so well, so it's actually for research, it's a good place to do study. If it works, then this is not interesting. And I do believe that legs will work someday, actually not very long. I mean, in 1 or 2 years, I feel like bipedal robots will become a very mature technique. given the progress we have right now. So sooner or later it's going to work. So wherever it works, then wherever we use, wherever it works. So if wheels works, we use wheels. If legs works, we use legs. There's not really argument here to why should we avoid these legs. And it has been a fascinating year in the field of humanoid robots. So this is, if you imagine, actually 2 years ago, when we say we work on humanoid robots in the community, so this is what we have seen usually. So this is the very common humanoid you might have seen a lot in the Mojoku simulation, and the task this guy is doing to going over the barriers. So this is not wrong. So it is going over all the barriers, but in a little bit strange pose, I would say. So this will be hardly transferred to the real world, and then and now I think all of a sudden I think it was very impressive to see a lot of great works that we have the Digit working in San Francisco, so showing a lot of other works as well, showing very robust policy and actually working in the real world. And then this is also a lot of work that's basically doing bimanual manipulation. This is actually already a while ago. But the cool thing about this, I always show is because as it is manipulating the object, it's not just moving its upper body, it's actually also having this lower body coordinating. So if you see again, you will see actually bend a little bit, the legs actually moves a little bit down. So it's not completely just upper body. So this is what we call whole body control. So basically the whole body coordinations, like legs and arms are coordinating together to finish some tasks. And essentially, this is something I will talk about today as well. So we talk about some whole body control work that we did. So essentially, how do you move your legs and arms together to do things? And if you look at the initial robot of this guy, so this guy is a H1 robot, maybe 1 year ago. So the initial ones we have is actually without hands. So now it got its hands. So I'm going to talk about some of our works that basically having basically the manipulation as well. How do you do bimanual manipulations with this humanoid robot? So mainly focusing on imitation learning from this teleoperation data. So once the data are all collected, so there needs to be some mechanism to do the learning. So although maybe right now it's not so related, but a little bit far related. But so this is because it's really a very exciting method. We have worked on it for so many years, and now becomes actually useful. So I would really like to talk about this as well. It's more like a machine learning new architecture that models sequence-to-sequence modeling. I'll make some connections that why this is useful for robots. But in general, this is modeling long context in linear complexity is universally useful for many different applications. Okay, so this is basically the things I want to talk about. And I would like first do some introduction of our robot work, specifically on the whole body control work. So this is an RSS paper done by Xixin and Yandong so about 1 year ago. And then I would like to show you a video. Hopefully it's not going to be too loud. So show you what we are doing. So it's trying to basically have motion imitating the person on the bottom. So if hopefully that's clear. So it went to right a little bit. If you see the video before, you don't have the second half of what's happening. So if you come to the talk, then you have the you see the whole thing. So it's almost boring, but it's not. So it's actually quite robust. So this is something that we want to optimize for, that this is robustness. Once there's something trigger, once it's going wrong, but it still can going to fall, but not really, and then recover. So this is what we want the robot to have. So here is a lot of scenarios that we basically run the robot, because we are in San Diego, so we have a beach, so we have to kind of run the robots every time we have demos. We kind of need to go to the beach to do some demonstrations. So this is just doing some parking motions. So here are some real results, but if you think about it, what has happened in the world of computer graphics and also gaming? I mean, you already have so many vivid motions of humanoids inside the game and simulations. So why is it not really transferring to the real world? Why is it stopping these beautiful wave motions transfer to the real world? So fundamentally, we need to clarify that actually nowadays, when we are talking about the hardware, the humanoid robot we have is not that like advanced yet. So it has very limited degree of freedom. So like I'm labeling the degree of freedom out in here, or labeling the joint out in here. So in total, there's like 19 or 20 degree of freedoms. So it's actually not as flexible as what we have in the simulations when we talk about the robot in the real world. So that becomes a barrier. That it actually physically impossible to do these kinds of motions in the real world. And then another thing is that it's very hard to do sim to real transfer from this motion in the simulation to real, because also not just because of degree of freedom. So the first row is showing that PHC and ASC are some amazing work from Jason, mainly in simulation, and you see the degree of freedom with compared to the real Unity robot is much less. The Unity robot has much less degree of freedom, but another important thing is like in the second box I highlighted with red, is all this privileged information we say we will obtain from simulators. So for example, linear velocity is always appear to be a very important observations. It's basically how fast the joint moves, or how fast the human moves. These observations. So the velocity of each joint. So this turns out to be an important parameters input for the policy. If you have these observations, a lot RL will just work very much better. And then, but unfortunately, in the real world, you cannot have these observations unless you have a motion capture system. So if you want to run the robot in the wild, you cannot really capture the velocity of each joint in open space. So I'll give you examples of what other people do. So it's so this is a robot maybe some of you have seen from Disney research. So this is a very cool work. So I was very impressed by this work, that it actually transfers the motions in the simulation to the real so well. So the reason, if you look into this one, is that if I play, if you look into this guy, there's these two dots in here. So people have worked on this field. It looks like this is kind of looking very much like motion capture system units. So essentially, in their setup, they actually have. So I kind of screenshot the line that's basically about the experiments that you need to have a motion capture setup to basically obtain these velocity observations. So in their case, they basically in simulation and real, they all have these velocity observations as input. So that allows them to do this kind of very good sim-to-real transfer. But again, if you want to run it in the wild, this is impossible almost. So on the other hand, also if you didn't notice, this is actually a very like not very large robot. It's actually less than 1 meter. So it's very hard to see in the video, but it's actually very short. So that also makes things much easier. So in our case, we want to work on full-size humanoid robots, and they also want to run it in the wild. So that these two things combined together makes the problem much more challenging. So we are basically going to train a policy that allows you to do that. Essentially, the policy is going to take a geometry, like a motion input. The motion is like a kinematics motion. So it's not a dynamics, it doesn't have dynamics, but the policy is going to output actions to ask the robot to imitate the input motion. So instead of imitating the whole motion, so first you have all these human skeleton motions, and then you do retargeting to obtain the robot motion. And the retargeting again is all geometry. So you just provide some mapping between human joints and robot joints, and then you ask the robot joints to fit the geometry provided by the human. But again, this is no dynamics. There's no, it doesn't work directly in the real world. It's just purely 3D joint locations provided. And your goal is to train a policy to convert these 3D joint locations to actual actuator action. So one thing we did in here, I think in the beginning, we think it is just a trick, but right now, I think this is very principally correct things to do, is that we're basically separating the imitations for upper body and lower body. So for the upper body, we still want to do imitation learning, because eventually we want the robot to imitate human to do different manipulation tasks. So you need to act like human to do these tasks. So we want the upper body motion to imitate human motion. But for the lower body, I think we really don't care actually how the humanoid moves. So as long as it works robustly, I think it's okay. So that's why we don't imitate completely. We don't imitate how human walks in the lower body, and this is actually more robust. I will show it later why. But essentially, we don't want to necessarily imitate how human walks, and then we separately just ask lower body run to use RL to train a robust walking policy. So essentially, this separation of the upper body and lower bodies turns out to be very useful. And then when you are controlling the robot, you can use a joystick to control where the robot moves around, and then upper body can imitate the human motion. So these two things are combined together to train a single policy. So the single policy actually, you basically, when you are running the policy, you provide two goals. One is where the joint should go, where the whole body should go, provide the velocity, and also what is the human motion, upper body motion, the humanoid wants to imitate. So if you have this objective provided the policy, and then you follow your commands to do the thing in the real world. So I would like to emphasize that the whole thing is actually training on a large scale, not so large scale, just hundreds of like motion, CMU mocap data set. So you have this human motion, you're retargeting to the robot motion, and then you train on all this robot motion. You basically want to train a policy that generalizes to all different kinds of motions. And then when you're doing testing, you can input any source motion, and then you're retargeting to the humanoid motion again, which is just a kinematics motion, and then you convert this motion into a real robot execution. So here is an example. So it's showing exactly what we do. So we essentially have this green dot as the reference motion, and then we want basically the policy to output the red joints that basically is following the green dots. So this is transferring to the real world. So it's not actually using any vision. It's just replay. It's basically just like executing the motion. It doesn't have like visual feedback here. And this is waving. And then again, the green dot is basically the reference motion. And then so it's running on the beach again. So we have to go to the beach. And this is a picture showing why actually learning from humans not that good for walking. So on the bottom, we basically show that when you are trying to learn walking from how human walking, you essentially you don't have a very large foot clearance. What we call is like how much distance your foot is above the ground. So because if you just think about maybe when you go after this talk, just watch yourself, and then you see. I mean, when you're walking, most of the time you don't actually you don't step your whole foot above the ground all the time. So that's actually something that is important for the robot to have robust walking, but on the other hand, it's not what we humans do most of the time. So we end up basically use RL to explore the right strategy to actually also encourage it to have a higher foot clearance as we show above. So it provides more robust walking. So this is a robust test examples that we basically, so in graphics, you will see a lot of like balls and throwing at the human now in simulation. Now we basically having it in work in the real world. So this is just a little bit also stress test that we push the robot and things like that. And then we also kind of managed to run, go to Santa Clara to run the robots to GTC, but we are only able to run it outside. We are not entering the conference. But we do have we do have lucky to encounter kind of fan in basically performing outside the conference, and then basically have the robot running some dance motions into the into this party. So it's kind of important to have these things though. I mean, we also have robots to attend some performance. Some professors work on human robot interactions and performance. So we have one performance actually a few months ago. So basically, we want to kind of advertising this like human and robot coexistence through art. So that turns out to be important because when we are releasing some robot videos online, a lot of people actually have fears like this is going to end the world, so we should kill it when we see it. So it's important to have some of these things. I think it's very interesting. So I will probably take a little bit questions after the manipulation part. So I think I'm running a little bit slow. So I quickly go through some manipulation work we do. And basically, so this is open television. The code is online. It's also done by Xiaolong and Xiaolong mainly. And then this is actually more about vision than robots, in my view. So this is, oops, what happened? Okay. So this is actually studying how to do teleoperation by having very immersive feedback, visual feedback. So we have a very cute design here. Essentially, you have installed a leg on the robot. So you have a camera in here, and it moves the same way as the human head moves. And this is streaming real time, what the stereo camera sees streaming to the VR views of this guy. So this is. So because the robot see the back of the humans, and then that wheel is streamed to your VR glasses in real time. So really, we spend a lot of time actually in this work to enable this like real time egocentric visual feedback into the VR by streaming. So the good thing about this is basically the real-time thing is important because like you can see that we actually do not have much latency when we are trying to tally up the robot. So what happens in here is essentially the Vision Pro detect your hand poses, your human hand poses, and then the human hand poses can be retargeting and convert to the robot hand poses, and then the command to the robot to do things. At the same time, the robot captures the vision and then stream back to the humans VR glasses. So the benefit of doing this is essentially you can actually control things remotely, like very remotely. So we have our collaborator, Ge, he's Phil's postdoc now. So he works in MIT, and then he's basically trying to do remote control of our the humanoid robot, which is in the US. He controlled it from Boston, like 3,000 miles away. So this is really teleoperating real time from very far away. So he did this pose because not because this is cool. It's because this is the command we use to finish the teleoperation. So if the Vision Pro detects this pose, then it knows that the task is finished. So once we collect a lot of this data, we basically can do imitation learning. So this allows us to, so this is actually running all autonomously. So it's kind of long horizon, although doing the same task again and again. So it's running the same policy very long time and keep doing it, repetitive kind of task, inserting the cans into the box. So you should see the camera is moving as well. So it has active vision. So I particularly like this part of the work. Is essentially you're looking at what we are working on. So you have kind of the vision is active. So essentially you take an image as input, and then you can train a policy using imitation learning, essentially supervised learning, the output, how the camera moves, and also how your arms and hands move. I like this video a lot because if you have ever worked on egocentric videos, like Ego 4D or Epic Chains many years ago, a lot of these egocentric videos, you see that actually this looks very, very much like of those videos. So you have your hands moving all the time, and then you see your two hands and doing things. So instead of human hands, you're now seeing the robot hand. So this is also the view that's streamed to the human as well. So as you are doing teleoperation, so it's really interesting because that connects a lot to the vision data, video data we have, and then it will be a very interesting problem to how to connect these two types of data to do better on these tasks. So it's a lot of examples that we can use a lot of robots. So this is just sorting different cans into different locations. So it's very simple task, but it's done continuously and very high precision. So we also showcase that if you do only teleoperations, it is not imitation learning. It also enables this sort of like very dexterous tasks that you actually pick up very small things into the box, and then you click the box, and then you finish the task. So again, all the time, human is doing it with egocentric vision feedback. So if you see the head on the top left, it's moving or focusing on the task you have. So human feels very intuitive. It's a very intuitive interface for humans to do this task. And here is doing some half wood work. So when you do 60 object pose estimation, you see a lot of people working on estimating the pose of the drill, but no one is actually ever use it. And then we basically show that we can actually use it. And again, egocentric feedback allows you to have very, very precise feedback. So human can actually see very details of parts of the objects, and then this allows you to do a very precise manipulation task. So we have some industrial integration of this system.
To accelerate Project Root, a general
The
humanoid
NVIDIA
robot
project
foundation model,
also kind of
NVIDIA
use
researchers
this,
capture human
this technique.
demonstrations,
So this
seeing
is
the robot's
Zhenjia,
hands in spatial
from
overlay
NVIDIA is
over the physical
doing
world.
some teleop using our system. So this is upper body, and if you remember why introducing the whole body control, we are essentially trying to disentangle upper body and lower body. Upper body is doing imitation learning, lower body is doing walking. Now we have the part that we can do teleoperation for upper body, and then we have the part that we can do robust walking. So can we combine them? So this is basically a recent submission that we do with the same set of people, but now we can do walking and manipulation at the same time. Compared to the previous work, the whole body work, so we continue to follow the strategy on separation of upper body and lower body. And then so we even go a little bit further. Actually, in the previous work, the upper body imitation are still using RL to track the motion. Right now, we just use IK and inverse kinematics and motion retargeting directly to set the positions of the upper body when we are doing the control. So we find this is actually even more accurate, like not using RL to do the tracking, but just directly setting the position for upper body. We have a little bit cute technique in here. So essentially, because now the upper body and lower body is quite separated, can you provide more information into the lower body control? How do you walk robustly? Like, how do you have robust walking given all these motions you do in upper body? So we basically have some technique that encode an embedding for the upper body, and then use that as a condition for the lower body RL policy. So now the lower body has a better understanding of what the upper body is doing, and then react accordingly. So this is a video. Essentially, we are running the robot outside. Unfortunately, we have this another robot that is actually losing its leg, so it's not functioning now. But these two, because we so we still make it play a part in our project as a patient. So this is just like pushing a wheelchair, and then you can do human as well, of course. So it's basically walking and pushing at the same time. All right, so that is this one, and then we actually do some useful tasks. So this is putting this box into the microwave. I'm not sure if it's obvious to you, but this is something we are actually standing still. Standing turns out to be actually a much harder problem compared to walking. So we actually spend like almost a year to enable standing somehow. So this is actually requires some upgrades from the hardware, and also particularly it needs to have 2 degrees of freedom for the feet. I will talk to that more if you are interested, but essentially some upgrade on the hardware and controls enables now we do standing, and now it's walking and manipulating. And here is another examples. So you often use a hanger to do experiments. So this is basically try to grasp a bag. So you walk to. So this is in our cafeteria in UC San Diego, and then you essentially. So this is all teleoperation. So there's a guy. You will see on the back, not this guy, but the guy in here. So this guy is controlling the manipulation. So again, you have egocentric vision feedback to the vision probe, and then you basically so you control the robot to put the things into the can, release it, and then go back, and then you go back. So yeah, so that's basically that's basically it's just an integration of two systems. It's not that simple as it looks, but it does enable a lot of usage that you actually become useful to do most of the tasks. So I guess that's the first part I want to talk about actually. So mostly about the control side, that we can do sim to real, we can collect data from the real world. So if you have any questions, please let me know about this line of research, and then I would go to quite a little bit different style of work. So I like to stop before that to answer some questions, and then we can move on. So if there are any questions.
We have questions.
Really cool presentation so far. Thank you. I was just curious about the size of the strides and the fact that the robot kind of very rhythmically steps up and down even when it's, almost standing in place, and just thinking
Right.
as a potential consumer, I feel like that would be kind of annoying because it would be very loud even if it was just like washing the dishes. And I'm just wondering if lengthening
Yeah.
and making them more appropriate to the distance it's traveling is a research direction.
I mean, are you saying is step the previous one that is actually stepping when it's standing? Like I don't know, like which one? Yeah, this one. Are you saying this one is a little bit annoying here? Is that the question?
Yeah, basically just it seems kind of not human in the fact that it takes
Right.
small steps.
Right. Yeah. I mean, that was both mixture of firmware, hardware, and software. So if you notice the feed before, is actually only have 1 degree of freedom. Let me pull out actually another slide that I want to explain this is better. So this is sorry. So you basically have like to actually properly stand, you need 2 degree of freedom. One is for pitch, one is for roll. So this you can move left and right a little bit. So maintain balance. So in the previous robots, it doesn't have roll, you only have pitch. So you only have this side of front and back kind of degree of freedom. So that actually stops it, makes it very hard to stand still. But in the new versions of the robots, so we actually kind of have both 2 degree of freedom, and that actually enables us to do the standing still. So, but then introduce new challenge in software design actually, because in the old ISAC gym, it doesn't model the linkage structure. So this is 2 degree freedom is basically it requires this kind of linkage structure to model it. In the old ISAC gym, it doesn't allow to model this kind of loop closure. But in the ISAC lab, apparently, so I heard this is solved. So previously, it's hard to model it. We kind of need to train a small liquid to have manual set up a function that convert this linkage structure into position control. So that also introduces some sim-to-real gap. So all these things combined together makes standing actually a very, very challenging problem. But again, we kind of managed to solve it eventually. So in this example particularly, it's actually standing still when doing the task. Yeah.
Makes sense. Thank you.
Right.
Hi. So I just have a question when you mentioned
Mhm.
separate the lower body and the upper body. Um,
Right.
is it a limitation of the hardware, or is there something inherently more robust or a better representation when you separate it? Or is it possible in the future to imitate whole body with a human with improvements in
Right.
the
Yeah, I think there's just I think I would say it's just more practical for now. Certainly, there's a lot of hardware constraint. So how many degree of freedom? I would imagine that if you are able to increase the degree of freedom, so we actually have very flexible robots, and then also somehow have a way to capture, like let's say the velocity of each joint. So you have more observations you can capture as inputs for the policy. So if you are able to enable these things, then um, the actual imitation for whole body will become much more possible. Right now, it's just we're missing these two parts, and then it makes very hard. So it is more practical now to have separating them and makes our life much easier. So particularly when we are doing this kind of manipulation again, um, so so using RL for lower body and just doing IK for upper body just enables much more precise manipulation. So not having RL um, to do the upper body thing actually still is more precise. So that's yeah. So that's very helpful. Yeah. Okay. Any more question?
Oh, I think there's one from the chat. So they're asking
Right.
how much time delay exists between Boston to UCSD? Was it critical, needing additional remedy?
No, it's actually quite good. I think I think the human operator does feel latency. Um, so um, so so he tried to act very fast, and
Okay,
then
sure.
I
And
was
then we'll
like,
get
we are
started.
like slow down, slow down. So there's a little bit latency, but a human can adapt. So I think it's 0.1 second kind of latency. It's not that a lot. So but if the latency occurs to like 0.5 second, then it's going to be very obvious and very hard to operate. So this is some places we can continue optimize, but currently I think it's already usable and adaptable for the operator. All right. So I can move on. So basically, so I'm not sure. Uh, the following part is a little bit more machine learning, but it's kind of motivated a lot of what on from the robotics side as well. If you look into a lot of this robot foundation model is doing is basically, oh, we train a big transformers to imitate everything, or train a big transformer to do word models and do predictive model. But transformer has its own problems, a lot of problems. So for example, if like, so we are also recently doing some navigation project. So if I want to just do navigation in an unseen environment, we are not having the map beforehand. So on the right is just illustration. We don't actually have the map beforehand. So how can we navigate to rooms, different rooms in the large house, and then also memorizing the environment without explicitly building a map? So we're using some VLM to do these things. So you basically hope the VLM can have a large memory. So here is a lot of examples that this is actually my house. So we are asking the robot to go out of this room and then go to my office. So actually, if you so on the top left, you basically, this is the visual input. So this is going to the office that I'm currently sitting in. Um, so so basically, um, if you want the robot to walk longer distance and then also have memory on all the locations and places he has seen, so that requires actually the uh, the vision foundation model to have a large memory or the capability to model long context. But transformer is just not that great at modeling long context and have a memory efficient. So it has quadratic complexity. So everyone knows about this, but let me just give you examples on like how and then strengthen your understanding basically. So let's say we want to do Lex token prediction, given this book. And then you say, oh, he was an old man who fished alone in the skiff in the blah, blah, blah. By him watching him, the old man was, you want to predict the next word. Okay, how do you predict the next word? Because you actually essentially want to do self-attention. So essentially you need to go through the whole text again to predict the next word. We're streaming, and then you predict the next word. What do? You again, the auto-regressive process actually requires you to read the whole book again about, and then you read the whole book again to predict next and next. So that's actually very, these examples make you feel like what we are doing is very silly, but that's actually what we are using in all places, not auto-regressive and with transformer. And this is certainly not how humans do it, right? So every time we think about what is going to happen next, we are not going to just read the whole book again. So in some sense, RNA is more clever. So it's actually have a memory of things, and then you basically just predict one word after another. So without actually going through the whole book again. So why are we not using the RNN and using transformers? So basically, actually, if you have read the scaling law paper, we basically see that RNN is not really scaling better with like larger legwork, with more parameters, more larger data sets. We gradually see that transformer is still like doing better. So it's not really good at long context as well. So when you increase the context to 8,000 more, then actually somehow a transformer is still doing better. So why is this happening? So fundamentally, we basically think that because like given this RNN architecture again, so this is machine learning 101. So you have ST-1, which is your memory, and then you want to update to ST, giving a new token over XT as input. So you update the memory. So it is very challenging for RNN to model long context because your hidden state is essentially just a fixed size vector. It's a fixed size vector. It's low dimension fixed size vector. If you want to compress all your context, like millions of tokens, into this fixed size vector, it's just a lot of things to do to compress. It's very, very challenging. On the other hand, you can actually represent your transformer into the architecture of recurrent neural network. So before we are doing some matrix multiplication to update the memory, transformer is basically saying, well, let's just not compress at all, right? So you're going with the KV catch. So you're just memorizing everything. Every time you have new tokens, you just append it. You're just memorizing. There's no compression at all. So on one hand, you're compressing into a fixed size vector. On the other hand, you're saying, oh, no compression at all. So that's what we are having in the models now. So our work is trying to answer that the question that is there any a better way to compress information into the hidden state, so we can have efficient inference in efficient autoregressive inference, and also potentially better performance. So now it's all about compression. How do you compress things? So let's give a vision examples as well. So let's say we have a bunch of tokens, image tokens, patch, and we want to compress it into a hidden state. And look at what we see if we do it in the larger scales, right? So if a bunch of data sets, so we want to compress it, what we do is actually training a neural network. So I think maybe 10 years ago when I say, oh, I guess I also do a job talk in here. So when I say when we want to do self-supervised tasks, we want to do unsupervised learning to compress the data, and people will say, oh, that's not going to work as well as supervised learning. but now I guess everyone agrees that like doing auto-encoding, doing self-supervised tasks actually can be a good way to compress your data set into a neural network. So so essentially you train, let's say, a diffusion model, you train a mass autoencoder with your data set, and then that gives you the model. The model can also generate new images, right? So we see all these astronaut on the horse a lot. So compressing is actually, it's really not just memorizing, but also generalizing, right? So this is, you can compose things and generate new things. So I think we are kind of all agree in the page that on the same page that actually doing auto-encoding training is a good way to compress or the large information of the images into neural network weights. So can we actually do the same thing? Let's go back to on the top. So once we have some tokens, can we represent these tokens by doing auto-encoding training, compress these tokens into model weights? So now the hidden state is not a feature or something, it's actually model weights. So this is similar to what we have done in NERV and implicit function, if you're familiar with that. So essentially you are compressing an image or scene into a small neural network, into MLP. So here is similar to that, not exactly the same, but similar, that we can use neural network training, construction training to compress information into model weights. So if you agree this is a reasonable approach to do compression, so can we do the same thing in the recurrent neural network? So essentially, like before, the hidden state is just a feature vector. So can we represent your hidden state as a neural network model? So what I'm saying now is like the ST or ST-1 is no longer just a vector. It's basically a neural network itself. So if it is a one-layer neural network, it becomes a matrix. If it's a two-layer MLP, it's two matrices. So we're using a neural network model to represent the hidden state. And then the update of the hidden state becomes neural network training. So let's say your current memory is WT-1, and then it comes in the new information, XT, and then you basically use this XT to have some loss. You train on this XT, and then you provide one step of gradient descent to update your model weight. So that WT is your new memory. So you are trying to use neural network training to inject the new information into the model weight, and then the new model weight is your memory, basically. So in particular, we are using reconstruction in here to do the training. So again, let's say you have a WT-1. This is a network. It has not seen XT. So if it is trying to do auto-encoding with XT, it will provide you some error. So now the loss, there will be a loss function when you try to do auto-encoding on XT. Now you basically use this loss function to provide gradient, and use this gradient to update your WT-1. So that essentially is injecting your information of XT into the model. So you updated the model weight as a new method, as a mechanism to update the memory of this model. So I'm going to stop a little bit in here to help you digest a little bit. But I don't have a lot of time. But I would just like to stop and then go ahead, and then maybe we can have QA later. But this is a part that's important to understand. Because we just keep going a little bit deeper later. But what you need to really kind of get, if you don't understand now, but what you really need to get is our memory is not a feature vector anymore. Our memory itself is a neural network, and we are updating the neural network as a way to update the memory. How do we update a neural network? We use gradient descent training to update the neural network. So that's what we are doing in here. So this is basically a new mechanism that we use to as a replacement for a self-attention block in the transformer. So in the transformer, you have MLP self-attention, MLP self-attention. Now we are basically replacing the self-attention part with our test time training layer. We call it test time training because it is essentially, as you're doing inferencing, you are using learning to update your memory. So you're learning at your test time. So again, you're using this neural network as the memory and use gradient descent to update the memory as you are taking more and more tokens. Now, that is the inference time. So this happens in every layer of the transformer. So it not only happens in the particular layer, so it's really just a replacement of your self-attention layer. So this is what we call inner loop because it's learning inside this neural network in test time. But we do actually have loss functions when we are doing the training, right? So we are optimally having the final loss function to do the Lex token prediction, to basically, so we still need to do the Lex token prediction to train the whole network. And the test time training inner loop is basically happening only like inside each block. So the loss function, reconstruction loss function in here. So the reconstruction function in here has, I think it's really not easy to do this online. So the loss function defined in here is actually not a parallel related to this one. So this is actually outer loop that the final goal you want to achieve. And this is what you use in every layer inner loop that you try to update your information. And then your training basically becomes actually, you want to learn all the blue part of the network. You learn the other parameters in the neural network so that when you do your test time training, it helps Lex token prediction. So essentially, you are learning all these parameters outside so that when you do this inner loop test time training, it helps the final goal of Lex token prediction. So this is going a little bit meta, basically. So you want to learn all the blue parameters, so it helps. Helps test time training to improve Lex token prediction. So what will happen is essentially mathematically, what happens is actually because you have a gradient in here. So as we backprop the gradient from here, you also backprop the gradient through here. So you would need to have a gradient of this gradient during your backprop. So there's a little bit second order gradient. But in practice, we have a dual form, basically convert this gradient computation into a simplified matrix multiplications that essentially kind of avoid this complex gradient computation. But within short amount of time, I want to say that basically, so this is a work that the key idea is still you should use a better way to model the memory. Now in here, we use neural network as a way to model the memory. And then as we are doing testing, we are keep updating the memory. And then the training is keep updating the memory by training. And the training is learn how to update the memory so that we can help Lex token prediction. So that's the overall idea of the work. And we did show basically improvements over the current linear complexity model like Mamba as well. So essentially, we train on books. Our biggest model is 1.3B. We show on the left, we show that as we're scaling the size of model from 125 million to 1.3B, so we have better slope compared to Mamba and Transformer. The perplexities, we are doing better, but Mamba and Transformer basically converge. And on the right, we basically show that with longer contexts, so we also have better performance. So the TTT linear essentially it's not converging yet. Like it's not converging to the transformer performance, but Mamba already converged to the transformer performance. So essentially, we are providing a better mechanism to model the memory in here. So and the speed is actually quite like reasonable. So we all, as the context time grows, because our prediction is conditional on memory, so it's almost remaining constant as your context name goes. So the actual inference time is similar to Mamba, and then transformer grow linearly because you need to do self-attention to more and more tokens. So here is just a brief overview. So if I can totally understand if there's a lot of questions about this. So just let me know if there are any questions, any place is not clear. But I think within such a short time, we want to just help maybe introduce the idea that the modeling of memory can have a lot of possibilities. It's not going to be just a fixed vector, or it should not be just a KV catch. It can be a machine learning model itself. And it can be now just a linear layer on MLP, but it can be a transformer itself. So the memory, the W in here, there's just a lot of possibilities. So you can think why the W can itself be a transformer to add that memory. So I think our goal is really try to explore this a lot more to actually to enable this memory more and more close to human brains and essentially that eventually we can model very long context instead of just like using KV catch to store everything. Yeah, I think that's all. Like, let me know if you have any questions.
Let's thank our speaker. Okay, thank you very much for the great talk, Professor. Maybe we have time for 1 or 2 questions from the audience.
Mm-hmm.
Oh, okay. Thank you for the great talk. I have a question regarding the demo of the second part, the first.
Mm-hmm.
Where does the delay come from mostly, and what are you storing for the demo? For the
What? Which one? This one? Which one?
Yes.
This one? Well, yeah. This is I didn't talk too much about this. So this is actually a system that we integrate both vision language models and low-level policy. So the VLM is actually running 1 Hertz, and then the low-level policy is running like real time. So there is basically need to be some communication. So what happens is actually you the VLM is predicting what we call is like a mid-level action. It's actually directly predicting, oh, the action is moving forward 75 cm, the action is turning 45 degrees, and then you have a low-level policy, which is also a visual policy that execute this thing in real time. There is a little bit of like stopping here due to basically the yeah, I think there is some delays there, and then we need to stop a little bit. But this is our system optimization we can continue to improve on. Yeah.
I have 1 question. So in the network you show with the RNN and the models being the memory, I know there's like an inner training loop and an outer training loop. Should there be like a specific relationship between the learning rates of those 2 different parts? Like, if there's something we should be aware of when we're trying to train this type of network?
Yeah. So essentially, so this is the parameter we need to tune. So this guy. So this is really the parameters, the learning rate. So I want to clarify. It's only doing 1 step of gradient descent every time it sees a new token. So yeah, we definitely have tuned a lot on this guy. So so I think the outer loop learning rate is fixed. This inner loop learning rate we did try to learn it as well. So we can also learn the learning rate so that if you do learning, it helps lexical prediction. So we kind of also try to learn this guy as well, but I think it didn't go so well. So I think we eventually just also do some hyperparameter search to get this constant. But yeah, that's a good question. That's this is some interesting space we can explore more. Ideally, we should learn this as well. How fast you should learn so that it helps lexical prediction. Yeah.
Thank you so much for the great talk. Let's take our speaker one more.
Thank you.